All right, in the last lecture what we did is we took a look at the flat plate boundary layer, and so we're looking at external flows, forced convection, and what we're going to do now is we're going to move on to external flows over bluff bodies. We're going to begin by looking at flow across cylinders. So looking at forced convection across cylinders, this is important to engineers for a number of different reasons. One of the most common applications within heat exchangers, cross-flow heat exchangers, are where you would have a tube bundle and flow coming across multiple cylinders, which we'll be taking a look at in a later lecture. But essentially what we have are a number of cylinders, so the flow over cylinders is of interest there. Another place could be mass flow sensors inside of automobiles for measuring the mass flow rate of air coming in. And a third application could be in the measurement of velocity for either experimental or HVAC applications, heating, ventilation, and air conditioning. And these are quite often referred to as being hot wire anemometry or hot wire anemometers. And so if you're looking at HVAC applications, you're measuring the velocity at a low frequency. And if you're doing experiments, you could be measuring it at a high frequency. And so the difference would be your cylinder would be much smaller in the case of an experiment. So anyway, those are three different applications of areas where we would have an interest in convective heat transfer over a cylinder. So let's begin by taking a look at what the flow field itself looks like. And so what we're going to do here, we're going to take a look at flow visualization. And there you can see on the top normal speed, on the bottom I'm going to slow it down. So that becomes slow motion. And you can see the red points there denote separation points. That's where the boundary layer is separating. And then downstream of there on this cylinder, we have what we refer to as being a very broad wake with a strong recirculation zone. And so this has a fairly large implication onto the convective heat transfer that will be taking place around the cylinder, because we only have attached flow on the front of the cylinder. And then once we hit the separation point, we have what we call separated flow, as you can see with the strong recirculation zones that exist. And so what we're going to do, let's begin by taking a look at what the flow field itself looks like on a cylinder, and then that will help us understand some of the physics in terms of the heat transfer. Okay, and so what I've drawn here is the flow over a cylinder up until a certain point. And what we have to begin with, let's see, we have the free stream out here on the left, and through Bernoulli's equation we know that the total pressure is going to equal the static pressure plus the dynamic pressure, which is 1/2 rho u infinity squared. And what I've drawn on the cylinder, I've drawn pressure taps at locations 1, 2, and 3, and these are static pressure taps. So they're measuring the static pressure in the boundary layer coming over the cylinder. And if we were to have an inviscid flow, which no flow would ever be that way, but if we had a flow without viscosity, what we would find is that the velocity on the top of the cylinder would equal 2 times u times the free stream, twice the free stream. Now in reality what happens is the boundary layer forms and the velocity does not behave in that way, as we'll see momentarily. But with this, what we could do with these static pressure taps, we can then say pressure wall at 1, so that would be static pressure wall at location 1 is the total pressure, we calculated the total pressure out here, minus 1/2 rho u1 squared. Now I've drawn this right at the front, and that would be a, oops, where did my cylinder go? There we go. That would be what we call a stagnation point, and so really the velocity there would be 0. But anyways, let's just say it's u1 for now. P wall location 2, again would be P naught minus 1/2 rho u2 squared. and then P wall at location 3, again the total pressure, minus 1/2 rho U3 squared. So what's happening here, the velocity is going from a very low velocity at the front, and the flow is accelerating as it comes around the cylinder. And consequently, what is happening is the static pressure is going lower and lower. And that's a region that we refer to as being a favorable pressure gradient, because as you're flowing along, the pressure is getting lower and lower. So the pressure is essentially pushing the fluid and causing it to accelerate. So if we were to look at the velocity at these different locations, we would have U1 is equal to 0, because that was what we call a stagnation point. And then U2 is greater than U1, obviously, because the flow is starting to move and accelerate around. And then U3 is greater than U2. And this represents the flow accelerating around the body. But from the flow visualization that we just saw, we saw a case where we had this broad wake and then a very large recirculation zone. And that does play a very big impact or part in what is happening with the flow around the cylinder. So let's take a look at what is going on with the pressure distribution around a cylinder. And so bear with me, I'm going to sketch out the pressure distribution here. It won't be the most accurate thing, but anyways, it'll give us an idea as to what is happening. Okay, so what we have, that's my best effort at being able to show the pressure distribution, not at all pretty. But anyways, what's going on? First of all, we have the inviscid curve. Now, inviscid, that's one that assumes that there is no separation on the cylinder. You can calculate this using potential flow theory, and that would be something that you would take in a fluid mechanics course. But basically you model the cylinder as a doublet with a free stream, and with that you can then come up with the shape and the pressure distribution around the cylinder. And what we find from that is we have a functional form for the pressure distribution. In reality, however, what is happening, if we look at our cylinder, the flow comes along, the stagnation point is at the front, everything is going good, but it will depend upon the nature of the boundary layer. So if the boundary layer on the cylinder, as the flow is coming up and around, is laminar, we get here, there will be a separation point if it's laminar, and if it's turbulent, the separation point will be further delayed on the back side of the cylinder. And that's why these two pressure distributions look different. And what we can see is that the turbulent boundary layer has a very different pressure distribution from, that says lamina, that should be laminar. We should have the R in there, the laminar boundary layer. So just by looking at the pressure distributions alone, we know that there's something different going on. Let's take a quick look at a schematic in terms of what this might look like. So if we have the laminar boundary layer, let me just sketch a cylinder here. So this would be the case of a laminar boundary layer. And for the laminar boundary layer, the separation point is at around theta equals 82 degrees. So that's typically where you will find the separation point with the cylinder if you have a laminar boundary layer forming. So we have our stagnation point right here. And then as the flow is moving up and around, we have a boundary layer forming. And if that boundary layer is laminar, separation will occur at about 82 degrees, and it is symmetric. So we would have a separation point at either of those locations. And what the separation point means is that the boundary layer is lifting off of the body. And so from the flow viz, you could see we had kind of the structures coming off. And then in the downstream, we had large-scale vertical structures. They call that the von Karman vortex street. But essentially, it's a broad wake in the downstream. And the implications to heat transfer is this region in the downstream is being impacted by the fact that you have all of this recirculating flow. So this here is a separation point. And if we were to look at the drag coefficient for a cylinder with a laminar boundary layer, it's around 1.2. Now it's going to depend upon the Reynolds number. You got to be careful because a very, very low Reynolds number would be what we call creeping flow, and it would be a very different drag coefficient. But that would be, I don't know, I'm guessing a couple thousand up to, I don't know what the transition, oh, here we have critical Reynolds number, 3 times 10 to the 5, so I'll be getting to that in a moment. Now, let's draw the cylinder again, and what I'm going to do here is, this case, we're going to assume that we have a different Reynolds number, and the Reynolds number here would be where we have a turbulent boundary layer. So this could occur in a number of different ways. Obviously, if the Reynolds number was higher, you can also sometimes trip the boundary layer on a cylinder. What you do is you either put a wire or sandpaper at the front, and that can cause the boundary layer to transition. But we would have our stagnation point. The boundary layer is forming around here, but let's say it then goes through transition. It becomes turbulent. When it goes to turbulent, what happens is the separation point, the flow is actually able to make it around the top of the cylinder. Here it is not. It separates before it gets to the top. But for the turbulent boundary layer, it's actually able to make it around the top of the cylinder. It's coming around to the backside. And at about 120 degrees, that's where we find separation for the turbulent boundary layer. So theta approximately 120 degrees. And with that, consequently, we have a much narrower wake, and that then consequently has implications onto the convective heat transfer on a cylinder. And so here CD 0.3 would be an approximation. This is why golf balls are dimpled. Golf balls are dimpled in order to cause the boundary layer to transition. And through the transitioning process, the drag coefficient goes down and golf balls fly much further than if you only had a laminar boundary layer forming on the golf ball. So that is the purpose of the dimples. They cause the boundary layer to transition. Okay, so where does that transition take place? The critical Reynolds number for a cylinder is about 3 times 10 to the 5, and so that would be Reynolds number based on, diameter, I would assume. Yeah, it must be. Okay, so 3 times 10 to the 5, and that is where we go through the transition process, and then your separation point moves further downstream. You have very different heat transfer characteristics. So that has an impact on convective heat transfer, and obviously that means that we need relationships that will then be a function of Reynolds number, and that's what we'll be seeing in a later segment of this lecture.